Hello, thank you for joining today's webinar. We're talking about creating high-performance embedded applications with a really high-end microprocessor architecture. It's a new architecture that we've developed specifically for this space. I'm Michael Thompson. I manage the high-end processors at Synopsys. So obviously, processors are near and dear to my heart. I've been involved in this activity for about 40 years, which is really interesting for me to see where this is going. At Synopsys, we have quite a range of processors available today, from the EM family, which is a very small pipeline but delivers very good performance, the SEM family designed for security, and we're seeing a dramatic increase in the need for security across all applications, embedded applications. Of course, the HS family that we've had available now for 8 years that delivers really fitting into the mid-range and high-end space in the embedded. Our new VPX family, which are vector DSP processors, and of course our EV family, which is targeted to vision and artificial intelligence applications. Of course, all these processors are available for a range of applications, including automotive applications. So I wanted to talk briefly about the applications that we're seeing driving high-end embedded performance. And of course, SSD drives or flash storage at the high end certainly is for enterprise applications. And that's, those drives are increasing very rapidly in size. You can get I believe the largest drive you can get today is about 60 terabytes, which is just a huge, huge space. And of course, that requires a number of changes in the underlying processors that are used for the controllers, the FTL layer and things like that. There's an increasing use of hardware accelerators. Of course, we're seeing compute and storage, AI and storage, those kinds of things, which have increased dramatically over the past few years. And of course, there's still a need there also for real-time processing. So it's a real challenging environment. Networking as well, with the growth of the internet, from the cloud to the edge and the endpoints to the internet. Intelligence is being distributed across that whole space now. We're seeing processing move, a lot of processing move from the cloud out to the endpoints of the internet, requiring larger address ranges, higher and more scalable processing. And then finally, wireless. And I listed 5G here because it really is kind of, in a way, maybe even a paradigm shift is the right way to put it in. How that whole cellular network operates, with tremendous increase in the number of connections, especially the spatial density connections that you can have per square kilometer, but also the number of connections on base stations and that. And this is driving a dramatic increase in hardware acceleration, multi-core implementation, and the need for scalability to address quite the range of application. So there's a number of challenges that we've faced over the years with embedded processors, in fact, processors in general, but especially with embedded processors. It used to be that with the next process node, you would see 2x higher performance and about half the power consumption. That really has gone away with advanced nodes now as we move down to 7 nanometer. It certainly kind of went away at 16 nanometer, but 7 nanometer especially, moving down to 5 nanometer and 3 nanometer. Logic speeds have been increasing faster than memory access times for years. At a 28 nanometer level, the fastest you can access the memories is about 1.4 gigahertz, which will greatly limit the maximum speed of a processor. And that's what is being shown here in the chart on the left. But at the same time, clock speeds in embedded designs have really topped out in the 1 to 2 gigahertz range. In fact, the bulk of designs are done at a gigahertz or less, and there's a few in that 1 to 2 gigahertz range. And yes, there are a few that go above that, but really they don't. And the reason they don't is because of the need to manage power consumption and area, which both increase with clock speed rather dramatically. But then at the same time, the requirements for performance in embedded applications is increasing, and in some cases rather dramatically, and that's because of increasing functionality. For instance, in an SSD drive, the size of the drive is increasing. We're putting compute in the drive. We're adding artificial intelligence. Features keep increasing, and just the competition on the marketplace continues to drive up performance. So it creates quite a challenge for embedded designers and for companies that are designing processors for embedded design. Hopefully that changed. There's a number of ways that we've addressed the performance requirements in the processors. Deepening the pipeline, for example, has allowed us to clock the processors much faster, but the returns on that are starting to diminish again because clock speeds aren't being increased in embedded applications. But a deeper pipeline allows us to do multi-cycle memory accessing, allowing, say, 2 or 3 cycles to access the memory, which can allow the processor to be clocked at a much higher speed than the memory access times. So the processor can be clocked faster, and which is one of the reasons why we can clock processors up to 2 gigahertz and a little beyond today for embedded applications. Superscalar implementation is something that is being widely used today. There's 2-issue, 3-issue machines. We've looked at this very closely. Our HS4 processors are all dual issue, and that allows us to increase performance by about 40% over a single issue machine. We've looked at 3-issue as well and don't see nearly as much increase in performance. It's an area we may pursue in the future, but right now we're not. Multi-threading is an interesting capability that's being exploited by a few companies. It tends to increase the area of the processor rather substantially because there's a lot of hardware overhead to support multi-threading, especially fine-grained multi-threading. But it is an area that can lead to a significant increase in performance. And then out-of-order execution is something that's very much pursued for very high-end processors. Processors are used on, PCs or servers, or for that matter, the main application processor in a cell phone. Most of those support full out-of-order execution. For embedded, it takes a lot of hardware to support that out-of-order execution, and we've opted more to support limited out-of-order, which can increase performance. It certainly does increase performance, but without increasing the area and power of the processor too much. Now, of course, caching has been done for as long as I've been involved in processors. Certainly since the late 70s and before. But caching allows us to bring the information very close to the processor, so it can be accessed in one cycle or a few cycles, as opposed to memory that's outside of the processor, which can take as many as 100 cycles to access. And so it certainly increases performance. Coherency in the L1 or L2 caches, again, increases performance by across a multi-core processor structure, making sure that information that any given core or CPU core in a processor cluster isn't using old information. And these are all methods that have been used to increase performance and are being used to increase performance and work well. And I suppose as we move forward into the future, we'll find other ways of increasing the processor performance. But in a lot of ways, all these methods that I've described above have been tapped out already. And we really can't go back to this well if you were to try to find additional performance. And there's a little bit, but not much. And of course, wider external buses is something which has grown over time, and that's just to make sure you can get the information into a processor and out of a processor without stalling the performance. Now, the implementation of wider pipelines, and we're seeing that with 64-bit now, and maybe we'll see 128-bit in the future. I don't know. There's nobody that I'm aware of that's doing that today. But 64-bit pipelines are great. In some applications, they certainly can increase performance. For the average application, you're not going to see much performance increase going from 32-bit to 64-bit. And I always encourage designers to look very carefully at their design and not just jump to 64-bit with the assumption it's going to give you more performance in your application, because in about 60 or 70% of the cases, it will not. Now, there's certainly some areas where it will if you're moving around a lot of data, or if you need a larger address space, that kind of thing, then you certainly can see higher performance. But it's an important aspect of the market, especially in many design areas, but it's not necessarily going to give you an increase in performance in your design. Now, one of the trends that we've been watching in the market, has been going on for about 20 years now, is the implementation of multiple CPU cores inside of a processor. So, dual core, quad core is very common today for a processor. And the use of multiple processors in a design has been increasing steadily over the past 20 years. 20 years ago, it was unusual to find more than a single processor inside of an SoC. Today, the average is in the range of 5 to 7 processors, and this is continuing to increase. And many of our customers are asking us for much larger multi-core structures. In addition, we're seeing the increased use of hardware accelerators. And hardware accelerators, as you know, are very dense, can be the highest performance, the smallest area, the lowest power consumption when you're implementing a design. The drawback, of course, with hardware accelerators is they're not programmable. They're easily reused, but they're not very easily changed. So there are some limitations there, but coupling hardware accelerators with processors can bring a much greater avenue of flexibility as well as programmability to the use of hardware accelerators. And we're seeing increased use of hardware accelerators across a broad range of embedded function in an application today. The HS5 and HS6 processors, we actually announced these back in early April. We really see these as the next generation of embedded processors. They deliver much higher performance. We also have support for 64-bit, which I said again is important, as well as 32-bit versions, so you can maximize area if you need to, or take advantage of 64-bit capabilities. These processors are scalable from 1 to 12 CPU cores, which is very unique right now in the embedded space. Most processors support up to 4 CPU cores. A few support up to 8. There's a number of challenges in supporting 12 that we've gone and fully re-architected the internal processor interconnect so we can support that and maintain clock speeds. These processors also support up to 16 hardware accelerators, and those are user hardware accelerators that can be easily attached internally through an internal interface to the processor to increase performance overall. The cluster interconnect that I mentioned, we developed from the ground up, supports 800 gigabits per second. That's gigabytes per second bandwidth. Typical processor today, quad-core processor, supports 30 to 40 gigabytes per second of internal bandwidth. So we've dramatically increased the internal bandwidth to support the number of CPU cores and hardware accelerators can be implemented with the processor. And that's important because otherwise you could stall out the performance of any CPU core or hardware accelerator, which we certainly don't want to do. These processors are backwards compatible with the existing ARC processors, the EM and HS processors. They're not binary compatible, but they are backwards compatible. You can easily compile code from existing ARC processors to be used on these. And of course, we have a full range of development tools that are optimized to support the processors. Now, this is a look at the specific processors that we have in this range. So the 64-bit processors are the HS66 and the HS68. The difference is that the HS66 does not have an MMU. It's really designed for real-time applications. The HS68 has support for an MMU. They're both available in single-core or multi-core processor implementations. The multi-core processor version can support up to 12 CPU cores. The 64-bit processors, both 66 and 68, have a 64-bit virtual and 52-bit physical address space. Now, a 52-bit physical address space is 4.5 petabytes. That's 4.5 times 10 to the 15, which is a huge space. It's larger than anybody's asking us for today. In fact, 44, 45, 46 bits is becoming common, up to 48. We're not seeing requests for 52, but we've designed these processors, again, for future applications to be usable into the future and to give embedded designers the capability to scale into the future as well. And these processors also support 128-bit loads and stores per clock, so you can move data very efficiently and quickly with the processor. At the 32-bit, and by the way, this is a full 64-bit pipeline register file set. It's full, processing units. The whole processor is 64-bit. The HS56, 57D, and 58, those are 32-bit processors with 32-bit pipeline and ALU and core registers supporting 64-bit load store instructions. The processors, if you use an MMU, will support a 40-bit physical address space. You do not need the MMU to support the 52-bit physical address space with the 66 or the 68. But with the HS5 processors, they'll support up to 32-bit without an MMU or 40-bit with an MMU. The HS57D adds additional signal processing instructions, depending on how you count them, up to about 150. To extend the performance of the signal processing capability with the processors. We have that available, of course, with the HS47D and some of the EM processors as well, and have quite a broad capability for the support in terms of software of signal processing that is fully supported with the HS57D. All these processors have a 16 megabyte shared cluster cache and L2 space. That can be partitioned between the shared cluster cache and the L2. The L2 can be up to 16 megabytes inside, or partitioned again with the shared cluster cache. And as I said, these are available in single and multi-core processor versions. So all ARC processors have been designed from the ground up for embedded application. This is absolutely true of these processors and future ARC processors. It'll be the same. We don't target, for example, PC processors, the main processor in a PC, although ARC processors are widely used in PCs and laptops. Typically in a laptop today, you'll find anywhere from 5 to 10 ARC processors inside of that laptop. In various functions there, but not in the main processor. We also don't target the main processor in cell phones. But again, ARC processors are widely used in cell phones, and the memory and the sensors and a lot of other functionality exists in those phones. Targeting embedded, we look for things where we implement things like single cycle peripheral and memory access, which induces the latency across the full system and improves overall system performance, and obviously improves the processor's performance. We have very large support for close-coupled memory, up to 16 megabytes each, instruction and data close-coupled memory. And we don't typically see customers using 16 megabytes. A couple megabytes today is kind of the top end, but if you need more, especially into the future, it's there. And this is a really nice capability for real-time applications because you can put all the whole program and the data that's required for the application in close-coupled memory. And that's single-cycle access for the processor, so you get very high performance, so the total performance out of the processor. And we have, as I mentioned, 128-bit load stores for the HS6 processors, 64-bit load stores per clock for the HS5 and HS4 processors, as well as the HS3 processors. All the HS processors support that rapid load store capability. And then the Apex custom instructions. So Apex is a capability that's supported across the whole ARC processor line. It allows the designers to add their hardware to the pipeline. And this is a different capability than adding a hardware accelerator. You can think of course, custom instructions and they can be used for, hardware to accelerate. But with a custom instruction, you're adding hardware to the pipeline itself with while the instruction is executed, it can block the pipeline. With the hardware accelerators, it's attached to the processor tightly for the new processors, but it's outside of the processor. It's not part of the pipeline. We have support for fast context switching with up to 8 register files. Again, under user control or designer control, you can implement 1 is the default. You can implement 2, 3, 4, whatever, up to 8 register files. And you can use that for fast context switching to move between different threads or interrupt, context switching, that kind of thing. You can do coarse-grained multi-threading with this, and we have a few customers that do that as well. And of course, we have a very robust interrupt architecture that's, again, programmable with auto-save and restore. So the HS58 and HS68, the new processors, both have include an MMU, a memory management unit. They're designed to run high-end operating systems like Linux, for example. We have support for the Linux kernel and SMP Linux or symmetric Linux for the multi-core processor implementations. And that is merged upstream into kernel.org. So if you download Linux from kernel.org, you get support for all the ARC processors that have support for Linux. And of course, we have full caching structure with up to 64K L1 caches that's programmable in size by the user, and up to 16 megabytes of L2 cache that's shared with that cluster memory capability. All these processors, the HS processors, are built on a 10-stage pipeline, and that's a very optimal pipeline for embedded applications. First of all, it allows two clocks to access the memory. It can be single clock if you want, or 2 clocks. That allows the processor to be clocked at twice the speed of the memory, so that you can get much higher processor performance by increasing the clock speed. We also have full MAC capability, sustaining 32 by 32 MAC per clock or dual 16 by 16 MACs per clock. We also have support for quad 16 by 16 MACs. And then, of course, a compiler, the MetaWare compiler, has been optimized to take advantage and schedule the instructions appropriately, so to maximize the performance through the HS pipelines. We've actually upgraded the MMU, or updated, maybe is the right word, or increased the capability there with a hardware page table walk. This MMU has support for concurrent page sizes, which is very attractive. It can be managed by Linux. So you have a normal page size up to 16 KB, and then a very large page size, so you can access big chunks of memory at a time up to 16 megabytes. And of course, the translation look-aside buffers, or TLBs and JTLBs, are very much optimized for performance, especially running Linux. And as I said, the HS5 and HS6 processors support up to 12 CPU cores per processor cluster, so you can get very high scalable performance. And of course, the new Interconnect will allow you to sustain that performance across a range of applications without stalling any of the processor cores or hardware accelerators. Now, at the same time, HS5 and HS6 processors can be used and will be used for real-time applications. And you can actually license, if you wanted, an HS68, and you can remove the MMU, and so you could use it with, running Linux in one instance on your SoC, take the MMU off and use it in another instance for real time. You can even not use cache if you want, and just put everything in the up to 16 megabytes of close coupled memory, both instruction and data. They're really ideal for that. They can be clocked. This is in 16 nanometer processes up to about 2.5 gigahertz typical. We see 1.8 gigahertz worst case. in those 16 nanometer processes, but you can sustain those clock speeds. And by the way, that's one of the things, one of the changes we made when we went to the larger multi-core implementation here with the 5 and 6X is that you can sustain those clock speeds with a multiprocessor, a multi-core CPU core implementation as well. Of course, have the high bandwidth load store capability and the other capabilities that I mentioned for embedded applications. But again, they can be easily used for hard real-time applications or real-time applications. We have a quality of service capability that's built into the multiprocessor, multi-core processor implementations. And all these processors can be supported with the Zephyr OS. That's an open source, a real-time operating system that has very broad support for real-time applications available online, or you can get it through, access it through a number of sources. Now, we've also upgraded and dramatically actually increased the performance of the floating point unit to reduce the latency. If you're using floating point, this is an optional capability that can be licensed to be used with the HS processors that substantially increase the performance by reducing latency. We've fully redesigned how the floating point unit interfaces into the 10-stage pipeline. You can see that over on the right, using a path forwarding or forward path capability that substantially reduces latency and allows us to have single cycle recovery. So we're seeing very good performance from this capability with substantial reduction in latency. But at the same time, if you attach this to the processor and this attaches to the processor pipeline, it'll increase the area by about, well, a little less than 50%. So it's a very good trade-off in terms of getting the floating point capability, but not increasing the area and power of the processor too much, or just a little bit. And this, by the way, supports half, single, and double precision operations, and that's all in hardware. And it's IEEE 754 compliant. So let me talk a little bit about the scalability of the HS5 and HS6, the new HS5 and HS6 processors. These support up to 12 CPU cores. That's HS CPU cores. Up to 16 user hardware accelerators. So whatever you want that accelerator can be, you can build it and attach it very easily through an interface that we have in the processor. The multi-core interconnect, as I said, has been completely redesigned or designed from the ground up, if you will, to support very high internal bandwidth speeds, but also very high external speeds, and to support the number of processor cores as well as the, number of CPU cores as well as the number of hardware accelerators. And that there's been a lot of change that's been made, a lot of innovation that's been built into this interconnect, and that's really one of the broad capabilities that we see moving forward in enabling higher performance capabilities in next generation embedded designs. And I mentioned already the QoS capability. I'll talk about that a little bit more a couple slides down. All these processors connect to an internal NoC. You connect them through an ACE interface, and they do support coherency with the NoC if that's something that you want to have. The design on the right there is just showing that you can have multiple HS5 or HS6 processors hanging on a NoC. They can operate coherently at the level 2, L2 level, and with other components on the NoC, we have the capability built in so that you can implement that very easily. All right, so this is a look at the interconnect, if you will. So just to walk through it really quickly, in the upper left, you see the HS processors, HS5, HS6 processors. to the right, you see user hardware accelerators. All the stuff in the purple color is things within the processor itself. The hardware accelerators, we provide the interface to those, but the hardware accelerators, of course, user defined. The network on chip is external to the processor as well. You see the network on chip or external interface to the processor can be AXI or ACE. It's up to the user to find the hardware accelerators attached through a coherent ACE-Lite port. And again, this is very scalable. So as a user, you can use, one HS processor and many hardware accelerators, up to 12 HS processors and one hardware or no hardware accelerators as you need in your design. If you connect to a NOC, great. If you don't, if it's just an internal AXI AMBA bus, that's also great. Both are supported. And there's a lot of other capability built into this that I'll talk about here as we move into the next slides. So the cluster itself is fully heterogeneous. You can implement, any combination of HS5 and HS6 processors for the HS processors. We don't see a lot of applications where that are use cases right now where that'll happen, but over time it may happen because of the flexibility that the architecture itself gives you. And of course, any hardware accelerator can be attached as long as it has the right ACE-Lite interface over here on the right. And of course, the external interface is up to the user, AXI or ACE. I've outlined here also the quality of service capability, which can be important for real-time applications, but can be used with other applications as well, so that the programmer can schedule the amount of bandwidth that any or each of the CPU cores gets to the interconnect, as well as hardware accelerators, so that you don't artificially diminish the performance of any of the CPU cores or hardware accelerators because they can't get enough bandwidth from the internal interconnect. And also the data bus widths, the channels that CPU cores connect to the interconnect and the hardware accelerator connect to the interconnect is scalable by the user, so as well as the external bus interfaces from 64 to 512 bits. So you have a lot of flexibility to determine, CPU core 1 maybe only needs a 64-bit interface, CPU core 2 needs 128 like that, or hardware accelerator needs 512-bit interface to increase the performance within the processor itself. But that, again, is controllable by the designer. We also have, and I've mentioned this, the local shared cache, and this L2 cache and cluster shared memory is a space that is partitioned by the user up to 16 megabytes total. So you can have, for example, 8 megabytes of L2 cache and 8 megabytes of cluster shared memory, or 16 megabytes of L2 cache and no cluster shared memory, however you want to use it. And that L2 cache will reduce the the latency in memory access, and it's a very large space for that reason, so that the CPU cores and hardware accelerators can directly access that memory space without having to go over the bus. And this is accessed in just a few clocks of latency, as opposed to potentially 100 or more if you have to go out on the bus. Oh, and this space can be dynamically allocated if someone wants to do that. There's a lot of coherency internally within the processor, so all the CPU cores can maintain L1 coherency. The hardware accelerators can be kept coherent with the L2 cache, as can the CPU cores, so you can easily share memory, if you will, between the CPU cores and the hardware accelerators, and make sure that there's coherency there. The L2 cache can also be kept coherent to a NOC with full SNOOP capability. There's a lot of capability here, and we see this going forward. The need for this is increasing just because of the complexity of the designs that are being done. But this certainly increases performance and makes it much easier for the programmers in terms of writing the code for the processors, hardware accelerators, and other capabilities that are built into the processor. Now, all of the CPU cores, as well as all the hardware accelerators, of course, can be implemented in their own power and clock domains. And this is a nice capability. First of all, it allows us to, the processors, CPU cores, to be operated asynchronously with the interconnect. And that has a couple of benefits. First of all, it greatly simplifies timing closure, which can be very difficult in a multi-core processor. If you've ever done one of those designs, we even see sometimes customers run into issues even with a quad-core processor, but you get to 8 cores and the issues can be almost insurmountable. But we, again, redesigned the interconnect to make that easy to achieve timing closure. This also, the asynchronous clocking allows for the a multi-core processor, even with up to 12 CPU cores and multiple hardware accelerators, to be clocked up to very close to the speeds of a single-core processor. And if you look today, you'll see in most multi-core processors, existing ones, you'll see a 10 to 20% degradation in maximum speed when you go to a multi-core processor, and that's because of the paths mostly through memory that are going to limit the performance, but also through the coherence units. But by making these asynchronous, you can manage that, get timing closure, and maintain very high speeds with a multi-core processor. We've also made a lot of effort to minimize the number of wire connects between the CPU cores and the interconnect itself to reduce the routing channel congestion and to just make the physical design easier to implement. Now, one of the capabilities we built in here is to take the data close coupled memory and map that into a single space for all the CPU cores as well as the hardware accelerators. So if you have a memory capability built into the hardware accelerators, because it's mapped into a single space, and each CPU core as well as each hardware accelerator has its own space in that, or own section of that memory space. For example, CPU core 1 could see and access the memory space in hardware accelerator 1, and that gives you a nice capability from a software standpoint to manage the hardware accelerators, because you can easily move data from a CPU core to the hardware accelerator, or from a hardware accelerator to a CPU core, for that matter, within hardware accelerators or within CPU cores. And it's a nice capability. Again, gives you a great deal of flexibility in how you manage and move data around inside of a very large processor cluster. And again, these channels are all configurable by the user from 64 to 512 bits width. Now, let me change gears here a little bit and just talk about some of the advantages that we see with a larger 12-core, 12 CPU core cluster. Of course, you're going to see better latency within the processor cluster itself, or between the CPU cores. Very uniform access times, especially with that quality of service capability that's built into the interconnect, and certainly higher speeds between the cores. Again, supporting up to 800 gigabytes per second aggregate interconnect speeds. Now, if we implemented that with 3 clusters of 4 cores, again, you're going to have 12 CPU cores, but to move data between any of the clusters, you're going to have to go out on the NOC, which has inherent latencies, as well as add traffic to the NOC itself, which is going to reduce system performance. And of course, snooping can be a great deal more difficult. It is possible to do between these clusters, but snooping cluster to cluster is a great deal more difficult with a NOC. In addition to higher performance, you're going to have much better software scaling. It's very easy to even dynamically partition the software, the applications across the cluster with a 12-core cluster. A little more difficult with 3 quad-core clusters. One, because you're going to get a little bit unpredictable performance. It's going to be much harder, difficult, and it's not going to be good at all for a real-time implementation. But with the 12-core CPU cluster, you have the flexibility to implement, use the cores, the internal CPU cores you need dynamically, and that's, reallocate the application load across the processors, maybe using, 2 processors for the application now, 6 later on. By the way, you can also dynamically control the speed of the CPU core. So if you have 2 cores running an application, you can run those at a gigahertz or maybe 2 gigahertz, while having another 6 processors running at a different speed with a different application. It gives you a great deal of flexibility in how you partition software across the cluster. Also, with the internal interface for hardware accelerators, and this, by the way, does not exist with most processors today, you get very nice access to the hardware accelerators, low latency, again, higher internal bandwidth and utilization. Because the L2 is shared between the CPU cores and the hardware accelerators, you can easily move data and make sure there's coherency within that data, and gives you very efficient control over the hardware accelerators, which you're not going to get with existing quad-core or higher processors, which most of those require you to attach the accelerator to the NOC. A few support maybe a single hardware interface. So the HS5 and HS6 are really designed to address the challenges that we're seeing our customers face with the increasing performance demands of embedded applications, delivering very high scalability with support for very large multi-core clusters, and it's been a request from many of our customers, as well as allowing the addition of up to 16 user-defined hardware accelerators. As I said, the existing cores support 2, 4, at the max 8 CPU cores, and you're going to find a lot of challenges in getting timing closure and limits in maximum speed with the existing 8 core processors. Also, again, there's limits on the number of hardware accelerators you can attach, at least internally, the processor, if there's any support for that at all. The cluster shared memory is an interesting capability. Again, we partition that space, that 16 megabyte space. You as a user can define that between cluster shared memory and L2 cache. This is something that's not supported on a lot of embedded processors today. We do support it on the HS3 and the HS4 processors, the existing ones, but a lot of competitive processors don't have this capability. It's a nice capability that allows you to move data very efficiently around inside of the processor itself, and also off to external memories or the NOC. Of course, support for the 52-bit physical address space on the HS6 processors, which again is 4.5 petabytes, or if you want 45,000 terabyte space, which is very large. These processors can be clocked, as I said, up to 2.5 gigahertz in a 16 nanometer process that's typical, 1.8 gigahertz worst case, which is very high clock speeds for the processors that are used in these applications. And of course, we have support for up to 8 register files or context, if you will, within these processors, including the 64-bit processors and the Apex custom instruction capability, which is available on all ARC processors. Now, the Apex custom instruction capability is included in all the CPU cores, and you can implement it on any of the CPU cores within the processor. But this is also supported with, in addition to the hardware accelerators, as I said. So you can have both capabilities running at the same time within a processor. Now, we have full tool support, including MetaWare, which is our a very optimized compiler for the ARC processors, supporting all the ARC processors. The Metalware Development Toolkit includes compiler debugger as well as instruction set simulator. We also have support for GNU, full support. When you download GNU off the web, you get support for the ARC processors. We upload any improvements that we've made to the GNU open source capability. We also have a range of, in addition to what's available in the Metalware Development Toolkits, instruction set simulators, as well as XCAM, which is a 100% cycle accurate simulator that's about 5 or 6 times faster than just using an RTL. And we have a range of development boards for software development and early prototyping, and then support for Linux, which I mentioned earlier, SMP Linux, and of course the Zephyr real-time operating system. This is just more information. We have full support for the GNU Linux environment with, you know, the kernel support, of course, from kernel.org. We maintain the GNU compilers for ARC processors as well as the debuggers. We have a team internally that does that with full development kit capability, as well as modeling capability with the virtual modeling capability for the ARC processors, and have support for a lot of the userland stuff that's available for Linux. So this is my last slide. It's just a summary slide. Again, we're very interested in working with our customers on the future of embedded processing, especially at the high end, but across the full range. The HS5 and HS6 processors are really bringing the future of embedded processing, that capability with very scalable and very high performance multi-core capability with 64-bit HS6 processors and 32-bit HS5 processors, all of which support up to 12 CPU cores and 16 hardware accelerators. The nice thing about these processors and all ARC processors is that they're configurable. The user can implement the processors how they need them in each instance in an application. They're deconfigurable, so you can license the processor with the MMU and remove the MMU in another instance in the SoC and use the processor as you need it for each specific implementation. Of course, these processors are designed not just with a view on the processor, but also with a view on the system performance overall. So there's a lot of capability to improve system performance, but also to improve the system implementation capability, and also the processor implementation itself in your design, improving timing closure with this fully redesigned interconnect. This is a very advanced capability that's not available with other processors today. So that is my last slide. I'd like to take some questions now. Let me see what we have. Hold on a second here. I have to click a few buttons. Okay, here's the first question. If you have questions, please go ahead and put them in through the question window, and we'll get to them, as many as we can here. So will larger multi-core solutions with more hardware accelerators be the main way that performance is increased for high-end embedded processors in the future? That's actually a very good question. The answer, I think, is yes, and certainly I like to say that because we're offering a very high-performance, scalable processor now with the 5X, 6X. I think that we'll also see additional ways of performance increased. It's hard to say what discoveries will be made as we go forward, but we really are tapping out some of the existing capabilities, at least from an embedded standpoint, because of the limits on area and power, or clock speed, if you will. So, things like, will we see more use of multi-threading? I expect. Will we see more use of out-of-order execution? Maybe. The problem with out-of-order execution is it increases the area quite a bit in relation to the processor, and it's not as scalable. You're kind of fixed at that point when that's implemented. But, other capabilities, absolutely, larger caching, especially L2 cache size and things like that. Yeah, we'll see that increase. But primarily going forward, it's going to be multi-core processor implementations with more hardware acceleration. That's certainly the way we're seeing with a lot of the application spaces, especially the ones that I highlighted at the front of this presentation. So the next question is, you mentioned that the new processors will have 3 times higher performance. Is it likely that performance will increase by 3 times, going from 4 CPU cores to 12? Somebody obviously read the slide, the small print on the slide, which is good. So that 3x increase is comparing quad-core to a 12 CPU core implementation. Now, in every application, you're not going to see that much performance increase. We've actually seen some application spaces where the increase was 4 times, and that's a little bit hard for me to get my head around, but you definitely can see up to 3 times performance gain. We have a number of benchmarks that we use to look at the performance of the processors as we're putting the processors together, the multi-core implementations, and a few of those do increase performance dramatically. But yeah, for most applications, you're probably going to see, I don't know, a couple times increase. It just depends on the application and how much of the task can be parallelized. So what is the available internal bandwidth of existing multi-core processors? It's a good question. Typically today, what we're seeing most processors is in the 30 to 50 gigabyte per second range. So you can see the 800 gigabytes per second is a huge departure from what exists today. And again, we implemented that in a way because we could, right? With fully re-architecting that interconnect allowed us to do so while, getting better time enclosure, reducing routing congestion, things like that. But also because we're designing these processors not just for today, but looking forward. As we bring more advanced processor capabilities into this, we can continue to use that interconnect or even scale it to higher performance capabilities. But certainly to support that level of processor, we need to have more than 50 gigabytes of internal processor bandwidth. So the next question is, hold on a second. Will the new processors be binary compatible with the existing ARC processors? No. So we actually, these new processors are implemented with the ARC version 3 instruction set architecture, or ARC v3 we call it. Existing EM and HS processors as well as the EV processors are implemented with ARC v2. So we've added some additional instructions and some additional functional capability in those instructions that wouldn't be supported by existing processors. So they're not binary compatible. They're very close. In fact, if you move code from an HS4 processor to an HS5 processor, potentially you could run the binaries, but we wouldn't recommend it because you wouldn't be able to take advantage of the more advanced capabilities that exist in the HS5 processor. So we always recommend our customers to recompile their code. But again, that's not a difficult task anymore with the advanced capabilities of compilers, including GNU. Why isn't there a 64-bit HS6 processor with support for the additional DSP instructions? That's a good question. So we actually looked very closely, and obviously we could implement 64-bit DSP capability, but we started asking the question, what do customers want when they move beyond 32-bit signal processing? And one of the conclusions we've come to is what they really want is a vector processing capability, which is our new VPX cores that I mentioned at the top end of this presentation. And what that allows a customer to do is scale the DSP capability from up to 512-bit wide vector DSP. And so we could implement, 64-bit DSP, but we're not sure it really is usable. What's probably more usable is having that vector capability, because when you go to a 64-bit processor and you're using, a larger cluster capability, you're almost certainly going to want if you need it, a much higher signal processing capability. That doesn't mean we won't implement it down the road, but for now we don't plan to. Okay. Oh yeah. So sorry, I'm reading the questions here. Can I license an HS68 processor that has an MMU and then use it in an application that doesn't need an MMU? And the answer is absolutely. And you can do that with the HS5 or HS4, HS3 processors too. That's one of the nice aspects of the ARC processors is that you can license a processor to run Linux, and then you can remove the MMU and use it in a real-time application. So in an SSD controller where you have the communication side processor as well as the flash translation layer processor, you can use the same processor, just take the MMU off and use it in the FTL layer, which are real-time, and use it with the MMU for the communication side, running Linux if you need it. But yeah, that's a nice feature that's capability that's available with all the ARC processors. We call it deconfigurability. It gives you just more for your money, if you will, more capability with the processor itself. Do you see the usage of floating point increasing in embedded applications? So again, a good question, and the answer is yes. Go back 10 years, especially 15, and floating point was used occasionally, maybe in 5 to 10% of designs. We're seeing that increase dramatically today. It's probably up into the range of 15 to 20% of designs now use floating point, especially as we move into advanced applications like 5G, where that kind of precision is becoming more important. And that's why we upgraded the floating point unit, adding half precision floating point to it, things like that, to increase that capability for our customers. Oh, here's a good question. Why do you support 16 accelerators, hardware accelerators, but only 12 CPU cores? So when one of the design metrics we had for these processors is that we wanted to maintain very high clock speeds in the multiprocessor implementation, and very similar to a single core, and we felt that was important for our customers. And we could have implemented 16 CPU cores, but when we did, we saw some degradation of the clock speed, and we're evaluating that. It's likely that in the future we'll support a larger number of CPU cores, but right now we've limited it to 12. We feel, first of all, none of our customers were asking for more than that at the moment. But we felt it was very important to be able to maintain that clock speed, and that was not an issue with the hardware accelerators, because with the CPU cores we maintain level 1 coherency across those cores. With the hardware accelerators, it's just level 2 coherency, so we can implement a larger number of hardware accelerators. And actually we limited that to 16 because we didn't see a need to go beyond that for most designs, at least not now. So why did you decide to support a 52-bit physical address space? Why not 64-bit? Again, a good question. 52-bit, first of all, as I said, is 4.5 petabytes. It's an extremely large space, and we don't have anybody asking us for anything near that today. We could have supported 64-bit, of course, but that adds additional hardware, and we didn't think it was useful for most of the applications that we're seeing and anticipate seeing over the next 5 years or so for the embedded space. So can I use Apex custom instructions and hardware accelerators at the same time? Absolutely. This is now understand the Apex custom instructions are on a per CPU core basis, so you attach those directly to the CPU core, and they execute in the pipeline. They look like they're part of the pipeline. The hardware accelerators are attached through an interface to the processor, and they're not part of the pipeline. They're attached tightly to the processor, and you can take advantage of the interconnect, the bandwidth speeds, and the L2 coherency, things like that. But they're not part of the process. So there's a fundamental difference there. But you can absolutely implement both Apex custom instructions and hardware accelerators at the same time. Okay, so let me see. So there's a question here. ARC HS5, HS6 processors, do we have a co-design environment for ASIP? So I didn't mention it here, but we do have a processor design tool that we call ASIP Designer that many of our customers do use to design hardware accelerators or programmable hardware accelerators if you want, because ASIP Designer does give you the ability to make that hardware programmable. But those can be easily attached to an HS5 or HS6 processor, and we expect to see a lot of customers doing that in the future. All right, let's see. We get one more question here. Let's see. Okay, so let me just, this one question. It's actually an interesting question. So it says, multi-core interconnect, is it part of the IP, the NoC as well? So with the HS5 and HS6, the multi-core interconnect is included with the MP version. So we have single core versions and then the MP versions. The NoC is not. That's completely separate. In fact, right now Synopsys has support for some of the AMBA interconnect, but it doesn't have a specific NoC. So we direct you to third party like Arteris, for example, whom we actually work with and have a very good relationship with. Okay, that's the last question I could take today. I will look at the other questions and try to respond to you appropriately via email or get one of the engineers if it's a little bit too technical a question, but we will get a response back to you. I do want to encourage you to fill out the survey as well, and I want to thank you very much for participating and listening to this presentation today. Of course, it will be available, recorded, available on the internet for later viewing. So thank you very much.